L-band's, unfortunately, probably not going anywhere. Beyond the Meteor constellation satellites that are going to be launched by Roscosmos, ESA and NOAA both have no plans to put L-band transponders on any of their new satellites moving forward. So whilst this is fun, it will be time limited. And you can 100% count on ESA to deorbit or decommission a MEDOP satellite while it's still fully working, because that's exactly what they did with MEDOP A. So moving on from there, I want to give a quick update on L-band geostationary stuff. So this is actually a slide from my last talk, but I liked it because up on the top left, it gives you a perspective of the Earth and all the various low Earth orbit weather satellites from a distance perspective, and then it shows you how far away geostationary orbit is in comparison. So basically, geostationary is what it says on the tin. From our perspective on the planet, these satellites are stationary in a single point in the sky. In actuality, that's not actually the case. Often they perturb around a point in a figure-8 perspective. It depends on how much fuel they have, how much station keeping they can do, et cetera, et cetera. Some geostationary satellites are better than others. Some satellites you cannot point to, leave your dish in the same spot and expect 12 hours later to have sync because it will have moved that much even though it's in geostationary. So geo's good because you can just leave the dish set up. Obviously, once you point and get a good signal to noise ratio, you don't have to track anything. The downside of geostationary is because things are further, you don't have as much signal strength, and so therefore your margin is lower in terms of getting lock. But what I would say is here in Australia, especially here in Western Australia, I feel like we're kind of in the Goldilocks zone for geostationary, if I'm going to be honest with you. So there are currently 2 Russian geostationary weather satellites within view of us, Electro L3 and Electro L4. There's also Fingyang 2G and 2H. Those are Chinese geostationary weather satellites in an older generation. There's also Fingyang 4A and 4B. They're also Chinese geostationary satellites, but a newer generation. We have what's now known as EWS-G2. NOAA basically takes old GOES satellites that they use over the continental United States. They basically run GOES east and GOES west, and then they have a hot spare in orbit as well in case one of them fails. Every time they send up a new satellite, they end up having a second spare. So what NOAA has done is that basically they hand that satellite over to the United States Space Force, and then Space Force pushes that thing over basically to the sort of over the Middle East and North Africa, and then it becomes a United States Space Force geostationary weather satellite. It's still the same GOES satellite. It's still unencrypted, still running the same services that it did historically. It's just now it's owned by the United States Space Force and is a military asset. Beyond EWS-G2, there's also GeoComSat-2A or GK-2A. That's a South Korean geostationary weather satellite. And then finally, there's Himawari 9, which is Japanese. You would probably recognize it because all of the bomb imagery that the Bureau of Meteorology uses from geostationary comes from Himawari 9. So if you go to their website and look at like the current satellite photo of Australia, that's where that data is coming from. So yeah, we're very lucky out here in terms of the number of geostationary targets that we have and the amount of data that we can get from them. So from my talk in 2023 to now, a couple things have changed with Electro L. Firstly, on the left-hand side, that's an Electro L3 image. In 2023, it never did a fully illuminated full disk image. For some reason, Roscosmos turned this on earlier this year. I don't know why. Nobody knows why in the hobby. I can tell you now that it's also off, so they're now no longer doing that time slot on a daily basis. But yeah, it's a bit weird. It was one of my biggest gripes about the satellite. It only does images every 3 hours, but it would never historically do the fully illuminated full disk image. Now it kind of does. And then on the right, this is Electro L4. This is the newest Electro L satellite that's been deployed by Roscosmos. As you can tell, it's further east from Electro L3. When New Zealand's not covered in cloud, you can actually see New Zealand pretty well. But yeah, that's an interesting satellite as well, just because it's nice to have options. Electro L3 is going to be replaced by L5 within, well, it was meant to already happen this month. That launch has not occurred. Roscosmos will get L5 up. When they do, they will drift that over to replace L3, and then they're going to take L3 and move it over to replace Electro L2, which we can't see. That basically sits over Western Europe. And it's beyond its X-band service. It's basically completely broken. So I can tell you right now, all the European hobbyists are very excited about the opportunity to start receiving that weather satellite. Moving forward from here, I want to quickly show you a few photos of stations that I've got. I'm not running all these anymore, but at the time I was. On the left, that was a GeoComsat 2A low-rate information transmission station. That satellite, that's the South Korean one I mentioned earlier, every 10 minutes it will send a single infrared IR 105 band image down. It's not great because it's infrared only, but because it transmits every 10 minutes, you can build very nice looking animations out of the imagery. In the middle, the sort of cream colored dish, that's my Electro L3 station. That's still running now. I've had that up since April of 2022. So I've collected a fair amount of Electro L geostationary imagery now. Enough to know that, yeah, that satellite is interesting because of its lack of reliability, in my opinion. Things are constantly changing with that thing, and often not for the better. On the right, this is a Newelec, basically GOES dish setup that I brought back from the States years ago. The two dishes on the left, you can see that I've got helical antennas on the front of them, well, helical feeds, I should say. On the right, this dish is a linear feed. So it's optimized for linear transmissions instead of helical transmissions. And because of that, those are very suitable for the Feng-Yang 2 series satellites, of which there are 2 still available. So moving on from here, after the B-Sides 2023 conference, that October was basically when EWS G1, which was originally GOES 13, was being replaced by in elevation to our west. Still plenty enough altitude for you to receive it with a good setup. Unfortunately, because I live up in the Perth Hills and I'm surrounded by trees, I can't get a 20-degree elevation lock on any satellite. Basically, about 30 degrees is about the lowest I can receive from my location. So yeah, I can no longer receive this. That being said, other people with a clear view to the west would be able to receive this fairly easily. It's a linear transmission. It's similar to what I was speaking to earlier. So that dish setup that I have there, that's a 1.8 meter prime dish. Because it's a prime, I threw a Cantana in front of it. Because it's an L-band Cantana, the dimensions are quite big. And yeah, it was pretty weird throwing that together because I finally realized my best bet was to go down to the local IGA and buy 2 of the very large Milo tins. Basically, I took one Milo tin, cut the bottom off the second one, wedged that one onto the first one to get it the proper length, and then threw an SMA flange, as they're called, which is basically a SMA connector with a metal rod attached to it, cut that to length, and that was my feed. So you might look at this and think, oh, that's incredibly technical, and it's like, no, it's literally 2 Milo tins slammed together with an AliExpress SMA that costs maybe $1. And yeah, this is what I was getting off of it. A bit of a funny story, we don't drink Milo in our house, but my son has a friend who does. So yeah, we had the really awkward situation where we showed up to school one morning and handed over 2 Ziploc bags full of brown powder to another parent, like while we were dropping the kids off, you know? And yeah, that was always, in hindsight, I thought maybe I shouldn't have done that, you know? Like maybe that wasn't the best of ideas, but hey, you know, like if I started telling people why I was doing it, I think they'd be even more concerned. Okay, so moving on from here, once I started investigating EWS-G2, I pretty quickly realized that, okay, well, this is a geostationary satellite operated by the US Space Force. They've got to have a ground station for this thing, but we're on the other side of the world from America. Where are they going to put this ground station? And the obvious answer is Western Australia. So up north from here, Swedish Space Corporation operates what's known as the Western Australian Space Centre. SSC is a private corporation that basically operates ground stations throughout the world for commercial services and governments to basically have satellite uplink and downlink capability. It kind of blew me away. I reached out to them out of nowhere and said, hey, I'm a weird dude in the Perth Hills receiving satellite imagery. Y'all want to catch up? And pretty quickly, oh yeah, the whole NOAA like ground station team's coming out in late October to commission the new satellite at the ground station, and why don't you come up and meet them? And I said, yeah, that would be really cool. So yeah, I got to drive about 5 hours up north. You can see up there is Geraldton, and then inland quite a bit is where the space center is. There's a lot of stuff up here in general. There's also ASD listening station up there. One of the guys that I met that was working at SSC had actually just resigned because he was going to the listening station to get a job. He had just accepted a job there and it was starting in 3 weeks. That was a fun conversation. Yeah, but it's quite a large facility with multiple dishes across the site. It also does some search and rescue work, which most of that stuff bounces off satellite as well. But yeah, very interesting to go up there. So while I was there, on the left, that's the NOAA/US Space Force dishes. These actually came from Wallops Island in Virginia, where NOAA has their ground station for if I'm not mistaken, the East Coast satellite goes east. They fully disassembled these satellites, shipped them to Western Australia, and then rebuilt them on the spot. When I was trying to organize to go up and visit, it was an interesting conversation because obviously this is a United States Space Force asset. That's U.S. military. I wasn't sure what, if anything, I would be able to see I drove up on the day when they told me to come up, and when I got up there, basically I was informed that morning, like, word had come through from Washington that, like, they could show me around. Up until then, they didn't know, which was pretty interesting. So, but honestly, I didn't care anyway, because there's more to the site than just the fenced-off NOAA U.S. Space Force ground station. But it was very good, because I ended up being able to go into the shelters, which are the little buildings you can see there. No photography in any of the shelters, but that's basically where all the hardware, all the ground station hardware runs, that basically receives and transmits to the satellite. Very interesting time. Very nice to meet the NOAA team. They were lovely people. I'd like to go back to the States sometime in the future and drop into Wallops and hopefully catch up with them again if I get the opportunity. While I was up there as well, in the middle of this image, you can see one dish pointing straight up. That's actually a SpaceX-owned asset. SpaceX uses that dish for Crew Dragon video downlink facilities. So basically, anytime SpaceX launches a Dragon capsule with people in it, anytime it's over the Indian Ocean region, all the video downlink from that capsule is received by this thing. You can't see it because I stupidly, actually you kind of can just see it. That's my car in the way, but just above the windscreen, you can see the Starlink Dishy terminal. That's how they're backhauling, because as you can imagine, the Telstra network connectivity up there is worse than garbage. So like, yeah, they're just like, no, we'll just throw, literally they just got the cable running from out of that little shelter there on the ground. Dish sits out there. And yeah, that's how they backhaul all the video back to the United States over the Starlink network. On the far right, you've got a JAXA owned dish. If I'm not mistaken, this is both C-band and X-band. JAXA uses this for launch telemetry. They use it for satellite station keeping. When I was there was actually a JAXA engineer there working in the shelter while I was being shown around, and it was awesome. Like, shoes outside the shelter door, you know, just like, I wish I could have gone in, because I reckon it would have been the cleanest and best shelter in the entire place. But yeah, unfortunately, because they were actually doing work at the time, the SSC people said, no, sorry, we can't go in there. I'm hoping to go back up and visit again in the near future, maybe in the next few months. I have reached out again, and I've touched base with them again, fingers crossed. ISRO, which is the Indian Space Agency, also utilized this site. That was really interesting. Like, in the main building there, they have some HP thin clients that we could probably go down to Ross's auction and buy like $30 a pop, as many as we want. That's what they're running their like tracking software on top of. Like, I love ISRO. Like, they run on a shoestring budget, and they do amazing things in space with it. So moving forward from there, I want to jump over here to a little bit of S-band weirdness, as I mentioned earlier. So there's a guy online called Scott Tilley. He's Canadian. I'm pretty sure he's up in British Columbia. His sort of claim to fame was Scott found a NASA satellite roughly a decade after they lost it, and it never worked for them, and he found it transmitting, sent him an email on the weekend saying, hey guys, I think I found your satellite, you know, and on Monday, like, his inbox just got swarmed with messages from researchers and, you know, other people who were basically just over the moon because the satellite was functional. They were able to get data off of it, and everybody was just like, oh, you know, we thought this was dead years ago, and like, yeah, you just, greatest Christmas present of all, right? You know, so in December 2023, Scott reached out to me. It's not that I'm anything special or am even very good at these things. I have dishes, I have hardware, and I can listen on multiple bands. So that, combined with the fact that I'm out here in Western Australia and there's not very many other people out here and we're pretty far away from everyone else, it makes it a useful place to look for things that obviously you can't see from North America because there's a planet in the way. So Scott reached out to me in December of 2023 and said, oh, the Chinese are launching a space plane. And basically what we were trying to do is find emissions from either the space plane or the objects that were deployed alongside of it, so we could basically get an idea of the orbital parameters with which that satellite was orbiting. There's a tool in the hobby called STRF, which is basically a Python software suite where you can take a baseband recording, combine that with accurate time and location via GPS, and compare that to TLEs from NORAD Space Track of all the objects that are currently orbiting the planet, and actually fit the object to a known, fit the transmission to a known object. So it allows you to sort of map who's transmitting what above you when they transmit it. So sitting out in the backyard, with my 1.2 meter with an S-band helix on it, looking for objects from the space plane. So this is, an image of SatDump. Over here I had gpredict up, and you can see that I basically imported all of the two-line elements for the space plane objects that we were looking at to see what transmissions they were potentially doing, to try to figure out basically what are they doing with the space plane and all these objects. Quite long into the pass, as you can see here, so it was starting to get quite low. It was just above 30 degrees elevation. I got this thonking signal, and I'm just like, wow, that just turned on out of nowhere, and that's really big and quite powerful, and it's on the frequency that we're looking for. Oh, I found either the Chinese space plane or one of their objects. So I sent the baseband recording to Scott Tilley in Canada. Scott used the STRF tools to try to fit it. Come to find out, Ubuntu NTP isn't very good, is the long and the short of it. At the time, I was running Ubuntu on my laptop because it was a fairly new laptop. Scott tried to massage the data as much as he could, and he's like, oh, I think I've got a reasonable fit, and it looks like that was object D. So Scott starts posting about this on Twitter. Other space news websites start picking up on it. I had to send a weird email to my mother saying, hey, there's screenshots from my Twitter, on the internet now, in the news, just in case you're aware, and come to find out my brother-in-law had already told her, which was very confusing. But moving on, we basically realized that it wasn't the Chinese space plane or any of the Chinese space plane companion objects. After a bit more work on time, and then me starting to do recordings on a Debian laptop instead of the Ubuntu one I was using at the time, we started to quickly realize that this transmission was from Yaogan 30X. Yaogan is the name of the Chinese spy satellite networks. There are multiple, so there's 30, 31, I think 34, 35, 36, 38, 39. They're into the 40s now. There are a lot of these birds up. They're all transmitting over Australia. The interesting thing about this that put Scott Tilley a bit on the back foot, and the reason why we sort of got confused initially, is none of this happens over North America. None of these satellites transmit on these frequencies above Canada ever. But here in Australia, all the time, from horizon to horizon, these things are loud as. It was a pretty interesting sort of thing. As you can see from here, Scott went back, redid some STRF analysis, identified it actually as Yaogan 30X. I started doing more recordings after that, just to do more STRF matching, just to confirm 100% it's Chinese satellite spy networks. It's all encrypted. Up in the top left, you can see the post where basically we provided the baseband recording to Alan, who's in his 20s. He's the lead developer of SatDump. He's in France. The best way I like to describe it is he sort of looks at satellite pictures, crosses his eyes like it's one of those 3D images, and he can sort of pull out the imagery out of it. He can basically decode stuff off the fly almost. It's a rare talent. But yeah, he built a decoder. We had a look. All the data is encrypted. And that's where I'm going to leave it, because I don't really know what else to tell you other than, yeah, they're doing this stuff above us, but over North America, they're not. All right. Now we're going to move over to X-band. This is my current X-band setup that's currently still set up in my backyard, well, in my driveway. So I'm going to quickly take you through this. That's a 1.2 meter offset dish. In front of it, I've got what's known as a waveguide. That's what takes the transmissions that get reflected off the dish. You might look at that waveguide and think, oh gosh, like what is that? And it's like, it's a 28 millimeter to 42 millimeter copper pipe reducer for plumbing, and 26 millimeter ID, 28 millimeter OD copper pipe with an end cap on the back of it, with a single SMA flange cut to length at 7.5 millimeters. It is not rocket surgery, this stuff at all. It's quite simple in theory. It's basically a cantana. So above that, you can kind of see a box. That's what this is. This is a different model though. This is a low noise amplifier for X-band. I got this from Down East Microwave. They're in Florida in the United States. Initially, and I'll show this to you in a couple of slides, initially I was using a single LNA. I wasn't able to get strong enough signal to noise ratio. About 6 months into X-band receiving, I started chaining LNAs, and that's when everything went good. So yeah, I now run 2 LNAs. You always run the first stage with the lowest noise floor. How RF chains work, basically, the first device that sets the noise floor sets it for the entire chain. So you use a low noise or a very low noise amplifier as your first stage. Second stage, you can basically put a microwave amp there. It doesn't need to have a low noise floor because that's already been set by your first component, and then that basically boosts up the signal. So as you can see, basically I've got one sticking up, and then it goes to a second one, which is this little guy right here. I picked this up off of eBay a while back. Should have unwrapped that beforehand. This is Narda Matek LNA, used off eBay. All of this componentry is going to run you at least $100 US used, plus shipping. A new LNA from the States, from Dimmy, is going to run you 150 to close to $200 US, excluding shipping. This is the first problem with X-band. It's not cheap. There's no sort of like wide hobbyist market to lower costs of sale. So yeah, it's a bit of a disappointment, but what are you going to do? Regardless, moving on, once you get through the low noise amplifier stages, you then need a down converter. Basically all the software defined radios that we use, unless you're going to buy one that costs what a car would cost, they're going to max out at 6 gigahertz. All of the X-band frequencies sit basically between 77 megahertz or 7.7 gigahertz up to roughly 8.4 gigahertz. So I need a device that basically takes X-band frequencies and then downshifts it to a lower frequency that my SDR can then listen to. So the LO of this down converter, which is hobbyist made from a guy named Arved, is 7,000. So effectively, whatever I'm listening to at any given time, the frequency gets downshifted 7,000, and that's what I listen to. So, but first, why do X-band? And the answer is so many channels. There's so much higher resolution and so many more instruments. These are all the current generation weather satellites from their respective countries. So this is a Mercy 2, the medium resolution spectral imager. This is on the Fingyung 3 Chinese satellites. As you can see, there's a ton of bands and there's very good resolution. Basically, the visible bands that you can see are 250 meter per pixel. Most of the infrared bands are 1 kilometer per pixel. So moving forward, started out in February 2024 doing X-band, immediately hit some problems. Top left, that's an image from Aqua, which is a United States X-band weather satellite. Aqua has no error correction. It has no FEC enabled on the transmission. So once you drop below 10 decibels in signal to noise ratio, you start getting drops from the satellite. So as you can see, multiple lines across that were where I actually dropped in SNR and couldn't maintain lock. On the bottom right, this is an image from Fingyung 3D. This was sampled at 50 million samples, or sorry, 45 million samples per second, which is quite grunty, let's be honest here. Once you start sampling at that rate, you start realizing that SSD and NVMe drives have buffers that fill and then start stuttering, and then you start getting drops, and it's not fun. So like, even though that reception that I did, I should have had ample signal to noise ratio the entire way. In actuality, I didn't, because I was having drops from my hardware. So, whoops, I just pushed past one. So once I started using the second stage LNA, I started getting much better imagery. This is from November 28th, 2024 from Aqua, that satellite that was the top left in the last one. As you can see, I was able to, for the most part, maintain like a high signal to noise ratio. You can see a couple blocks up there and then a little band up there where I dropped. But yeah, this is sort of what you can expect to get from Aqua, which is part of the Earth observing system constellation. There was Aqua, Terra, which has unfortunately now failed, and then there's also Aura, but Aura doesn't do any visible band imagery, so I don't have anything to show you from it. So moving on from here, this is Suomi NPP. So Suomi was the first satellite in what's known as the JPSS constellation, the Joint Polar Satellite System, I believe it's called. This is the current generation NOAA low Earth orbit weather satellite system. Suomi and NOAA 20, or JPSS-1 as it's known, both have severe nulls in their transmissions. And basically what that means is at certain elevations throughout the pass, the antenna on the satellite basically doesn't transmit as well as one would like. It encounters a null, and therefore the result is you get a drop in signal to noise ratio when you're receiving that transmission, and then once it passes the null, the signal to noise ratio increases again. You could have a perfectly fine lock. It doesn't matter, the null's gonna get you. So you need to have ample amplification to basically overcome the nulls. Yeah. So this is NOAA 21 or JPSS-2. With NOAA 21, when they launched this, basically it solved a lot of the Suomi and NOAA 20 null issues. This is also a little bit of a higher resolution. So for Suomi and NOAA 20, I sample at roughly 25 million samples a second because the signal's at roughly 15 megahertz in terms of width. So NOAA 21, for instance, is 25 million symbols per second. So I sample at 40 million samples a second. It does a true color image, which you can see on the bottom left, but that's a lower resolution image in terms of like the visible bands. On the right, this is a 321-221 composite, which is actually much higher resolution in comparison in terms of pixels per square kilometer. So moving on from there, as I said, instruments and more channels are good. So this is an example from NOAA 21, the fire temperature RGB composite. So in SatDump, when you've received the imagery and you go to process it, there are multiple composites that are available that are pre-configured, and you can say, all right, give me the fire temperature RGB composite. And so as you can see here in this middle image, you can basically see those spots on the image. That's actually the hot spots from the imager from the satellite that correspond with the fire that's currently taking place in the visible imagery. These satellites are what BOM and Bushfire IO use for our fire prediction stuff. So like if you're looking at Bushfire IO at a fire and you see a bunch of small dots, those small dots are sample measurements from NOAA 20, NOAA 21, and Suomi. The larger dots are from Himawari, the geostationary satellite. And the reason why is because the lower Earth orbit satellites have a higher resolution, so the dots are smaller, so because they can see basically 250 meters per square pixel, whereas Himawari up in geostationary can basically only resolve at 1 square kilometer per pixel. So next time you look at a fire, you can realize that, like, you can actually click on the individual dots and it will tell you, oh, this one came from NOAA 20, oh, this one came from Suomi, and it'll tell you the date and the time. Or you could just stand in your driveway and do it in real time like a normal person. So now we're going to move on to the Chinese low Earth orbit X-band weather satellites, the Fingyong 3 series. I got to be honest with you, China is flexing. These satellites are phenomenal from a visible band perspective, as well as from a multiple instruments perspective. So as you can see here, yeah, that's Fingyong 3D from August 1st, 2025. Here's a bit of a zoom in from down south. It's just absolutely phenomenal imagery. 250 meters per pixel per 250 meters squared per pixel image resolution, and you can get full true color composites off of it. Fingyong 3E was the next one that was launched. It has Zuvi on it, which is a solar imager. So you can basically download images of the sun in near real time. You can also build animations because it sends multiple images. At the end of this, I'll probably throw up a quick animation to show you what that looks like. I didn't want to embed it because I tried to, and I'm using LibreOffice, and it basically crashed my entire computer. 11 megabyte GIF, and yeah, it's 2025. It's cool. Fingyong 3F, this is another one of the 3 series. This does morning passes. So 3D is basically the afternoon satellite, so it comes anywhere between 2:30 and 3:30. This comes anywhere between sort of 9:30 to 10:30-ish. This has the Mercy 3 imager on it, which is slightly better than the Mercy 2 instrument that Fingyong 3D runs. And yeah, they're just phenomenal imagery. And yeah, the morning passes are quite good. Fingyong 3G is weird. It's basically a sideways sat. Instead of in a polar orbit, this thing is in a drifting orbit. It requires reboosting as well because it's quite low. It's only roughly 400 kilometers above the planet. Every time it reboosts, you lose transmission at that time. But it's a really interesting satellite. Also wanted to quickly show on the left, that's not a corrected image. On the right, that is a corrected image. So on the left, that's basically what the imager sees 1-to-1. But then because of the curvature of the Earth, you actually can correct out that image to make it look like a proper map. And that's what I've done on the right. So basically all the images, bar the one on the left that I've shown so far, have been corrected images. All right, Fingyong 3H. This just launched September 26th. A little over 2 weeks later, on October 12th, people in the hobby started getting images from it. I got this on the 14th. Yeah, really good satellite. This is the replacement for Fingyong 3D. So the first of the Fingyongs I showed you with that gorgeous imagery, this is its replacement because that thing's been up for 8 years. China's not playing. Yeah, 3H is very crisp, really pretty, great resolution imagery. Okay, X-band GEO. Yeah, I got a dish problem, as I mentioned earlier. It was not fun driving this 2.3 meter prime home in the back of a trailer down Row Highway. I don't want to do that again. But I needed a big dish because GeoCommSat 2A has an X-band ultra high rate information transmission service. This is what's known as a cast, so it's not raw data from the satellite. This has actually been transmitted down to a ground station, transmitted back up to the satellite, and then rebroadcast back down again. But this is basically their commercial service that I'm not paying for, and it's the best service that they offer from their satellite. So the transmissions roughly just over 15 megahertz in width, so I sample this at 31 million samples a second. Here's a bit of an image of what it looks like when I'm recording it. It's on 8070 megahertz. On the right gives you an idea of one transmission in terms of the data we're dealing with. It does this every 10 minutes. This is just the full disk imagery. It also has additional data. The SatDump team hasn't even started decoding that data yet. This is just the global full disk images. So yeah, lots of bands, 4 visible, 12 infrared, 16 channels in total. The visible images are anywhere from half a kilometer to 1 kilometer per pixel, and then 2 kilometers for the infrared channels. So on Monday, I was chatting with some of the developers in the SatDump team, and I asked them for a true color composite from this satellite. This is what I got. This basically uses the visible number 6 image, which is the half a kilometer per pixel, but that's a mono or a panchromatic image, I believe it's called. So looking at it alone, even though it's very high resolution isn't that interesting. But you can take the RGB channels, the other channels, and combine that with the panchromatic image in a process called panchromatic sharpening, and you can build absolutely massive composites. So this one PNG file is 1.13 gigabyte in size. This was one 10-minute time slot transmission from GK2A. There's a crop of just Australia. Zoom in, looks pretty good to me. And then, yeah, it's a full disk of the planet. So, like, yeah, it's quite good resolution. So, yeah. Basically, I'm going to throw this up and say, here's some places to learn more things. There are Discord servers. There are a couple of YouTube channels that are really good. There are some guides on the web. I'm here for all day today and tomorrow. As you can probably tell by now, I'm very comfortable in talking about this stuff. I would love to talk to you about it, if you're willing to put yourself through it. So yeah, I guess from there, I'll quickly say what's next. I've got a new toy. This is called a RF-NM. RF Not Magic is basically what it stands for. This can do 128 million samples per second. ESA just launched MEDOP SGA1. I've tried it a couple times. I'm going to have to tune my setup a bit, but yeah, fairly soon I'll have the new, hopefully, MEDOP ESA satellite as well. I think we're running pretty close to time. We might have enough time for a question or two, if that's okay. Yeah. So, anybody have any questions? Yes. Oh, okay. You know, that's a great question. So basically, there are 2 rough designs for dishes. There's a prime dish and an offset dish. So a prime dish effectively means the dish is designed to reflect all of the data it's receiving to a centralized point at the center of the dish. An offset dish is offset. So instead of reflecting it to the center of the dish, it actually is designed to reflect it to an offset point. So the beauty of an offset dish is your actual feed and all of your other equipment, the receiving end of the dish setup, is actually not in line blocking any of the radio waves that are coming in. I find for smaller setups, but yeah, when it comes to to geostationary, I find primes a little bit better, just because, yeah, you can use a prime feed. Your feeds also have to be designed to the dish as well. It's complex. Come and talk to me. Other questions? Yes. Yes. Yeah. Yes. So those big dishes for U.S. Space Force, they're hurricane rated. So like literally a hurricane could be coming through that point, a category 5. That dish is designed to stay stationary and functional during that weather event. But it's a very good comment, because basically the person who took me through the station from SSC had spent the 2 days before that giving the NOAA team a ton of grief, because he's like, oh, well, Drew's coming up and he's doing what you're doing with a 1.5 in his backyard. Like, why do you need these huge dishes, guys? What are you doing? So yeah, it was good. They found it quite funny that, like, yeah, I was basically receiving their stuff on, you know, an order of magnitude less size hardware. We good? We're good. Excellent. All right. Thank you, everybody.
The prestigious Space Challenge
The challenge coin. Thank you.
Cool.
Sure.
We'll just do the handovers now. Just a point of note, by the way, the live stream camera is just here, pointing across, so slope that way if you don't want to be on the feed. It's better that way because it means we can get easy access at the front. So just give us a second.